Let's consider a puzzling question using Digital Fire Insight. I'm going to double-click this Wollastonite, and we'll take a closer look at it. Notice that it has 1 part calcium and 1 part silica. So that means it's 50-50, supposedly. But in the recipe on the left, I have calcium carbonate 20 and silica 20. And so I've replaced those with 40 wollastonite on the recipe on the right. The other two ingredients are the same. But if we look at the chemistry down here, the calcium oxide is up by quite a bit, and the silicon dioxide is way down. Now, why is that? We're dealing with a viewpoint issue here because in recipes, we weigh material powders and we compare them by their weights, whereas in formulas, we are comparing numbers of molecules. Now, we know what these oxides do in fired glazes, and we relate the degree of their influence to their numbers in the formula. So let's double-click this and have a look at the oxides dialog and compare a couple. For example, take a look at lithium oxide. It has 29.8, a weight of 29.8. Compare that with barium, 153. So obviously there's going to be a lot more LiO2 oxide molecules in a given weight than there will be of BaO, and that accounts for why it's so much stronger flux. Let's compare CaO 56.1 with SiO2 60.0. So they're about the same. But remember, they're about the same as oxides, not as materials. As the materials that deliver them have their own issues. How about sodium and potassium? Potassium is 94.2, sodium 62. And yet these two oxides have very similar influences on glazes, but they exert those influences by numbers of molecules, and so you have to substitute them, keeping that in mind. Let's look at the barium again, 153. Now, strontium is often substituted for barium, but it's only 103. So this has to be taken into account. So let's close this. Another dynamic is loss on ignition. Now, if I double-click Wollastonite here to bring up the materials dialog, notice that it has a 0 LOI. Now let's compare that with calcium carbonate. 43.9% of that goes up the chimney during firing as gases. So only the remainder is supplying the CaO. So even if I could deem the powders, the calcium carbonate powder and the wollastonite powder, to contribute equal amounts of CaO, this messes up that assumption because a lot of it is lost, a lot of the calcium carbonate is lost during firing. So I'll close this dialog. And another dynamic is that these formulas are calculating to flux unity. That is what these asterisks mean. So if I change any value in this formula, all of the others are going to change in order to recalculate that flux unity. So that's kind of like percent. If I change the amount of calcium carbonate to 25, for example, here, and then I recalculated the rest to total 100, then all of the numbers would change. So to level the playing field when substituting materials, we set these at no unity. And now notice what happens if I select the wollastonite, recipe 2 here, and watch the CaO line. As I bump the wollastonite up, the CaO changes and the SiO2, because that are the two oxides that it is contributing. But notice that none of the others are changing, and that's what we want. So I'll put that back down to 40. Now with the calculation set on no unity, let's just compare these formulas again. Notice the calcium oxide is way up, and that's kind of expected because we have 40 grams of wollastonite versus 20 of calcium carbonate. And notice the silica is practically the same. So that means 40 grams of wollastonite supplies about the same amount of SiO2 as 20 of silica powder. Now let's do this substitution correctly. I want to supply CaO from wollastonite equal to that being supplied by calcium carbonate. So I've got recipe 2 selected. I'm going to click the supply button and I'll tell it that I want CaO. It already knows that I want 0.2, so I'll go done. So it has calculated that I need 23.24 to match up my calcium oxide. And now I need some silica. So let's go up here and I'll click supply. Silica is already chosen. It already knows what I need by looking at recipe 1. I'll click done. And now it's matched. So now let's set these back at RO unity. So now we can see that to correctly replace 20 calcium carbonate, we had to use 23.24 wollastonite, and we had to reduce the silica by 12, so now it's 8 instead of 20. So this task of substituting wollastonite for calcium carbonate demonstrates some of the important issues that you face when you are substituting materials. But if you go to digitalfire.com and you click on tutorial videos, down near the bottom here, there's a number of other videos on this topic. Here's one for feldspar and nepheline. And this one here, substitution rules for whiting and wollastonite, goes into much more detail than we have now. Here's one for substituting Guernsey borate. And so this will give you lots of information on how to do it properly and not just expect that you can weigh out powders gram for gram and substitute one material for another.